Okay, example 9, find the exponential decay function for the amount of phosphorus-32 that remains in a sample after T days. And you guys don't have to open up your book to this page. I'll do mine, but just know where it's at. On page 425, you might want to write that on your sheets. Page 425 is the magic page in the book that has half-lives for different radioactive substances, one of them being phosphorus-32. And if you looked on page 425, you'd see the phosphorus-32 half-life is 14 days. And some half-lives are in years, some are in days. Polonium-214, if you're interested, is 1/10,000th of a second. I don't know how much science you guys have done, but if we don't understand half-life, let me give you a quick example. If this is 5 pounds,
it'll be 2.5.
5 pounds of phosphorus-32, after 14 days, I'm going to be down to 2.5 pounds. Okay, so if I just set it in a pile and just say, you go over there for a while, wait 14 days, in 14 days I got 2.5 pounds. 14 more days I'm going to have 1.25 pounds. And nobody's stealing it, it's just decaying, it's going away. Radioactive material decays, it dissipates over time. Polonium-214, 1/10,000th of a second. So if you had 5 pounds of polonium-214, 2/1000th of a second, or 1/10,000th of a second, I'm down to 2.5 pounds. Another 1/10,000th of a second, that's 0.0001 seconds.
And then another 1.6.
0.0001 seconds more, and so on. So after about a minute, or even let's say a second, it's going to halve itself 10,000 times. I don't even know how they know that exists. It wouldn't stick around long enough to see it. But anyway.
Is the next one 0.625?
Yeah, 625 maybe.
Yeah,
we have
will
that.
it ever be completely zero though, since it's always happening sometimes?
Well, I suppose, but at some point it gets down so small,
Yeah.
it might as well not be there.
Yeah.
Yeah. So imagine you had a pile of polonium-214 as big as this school. I'd say within 2 seconds you wouldn't even be able to see it anymore. That's how quickly it's dissipating. It might only take a second also. Half itself 10,000 times in 1 second. Yeah, probably gone after 1 second. Just interesting. But anyway, phosphorus-32 is what we're dealing with here. Half-life is 14 days. And they want the exponential decay function. So again, they told me to use decay function, and right there on the sheet very clearly states decay function is the same as the growth function, right? Mm-hmm. The final amount is equal to the initial amount, e to the kt power. All right? The issue here is they didn't tell me anything, right? They gave me nothing. They didn't give me a time, they didn't give me a final amount, initial amount, anything like that. So when they don't do that, if you're dealing with a radioactive material and you know its half-life, this is how you can figure out some stuff. All right? I'll put n sub 0 equals, n sub t equals, and t equals. All right, those are the three things. We again want to find k. The difference between a growth and a decay for k is in a growth function, k is positive like it was in example 7. In a decay function, k is going to be negative. Let the numbers work themselves out. K is going to come out negative as decay. It'll come out positive as growth. You don't have to say, oh, it's supposed to be positive, let's make it positive. No, it's supposed to be positive or negative, and make sure that it happens as it should. So here's how you do this on a radioactive material. It's real simple. Whatever the half-life is, 14 days, use that as your time. And as long as your final amount is half as big as your initial amount, you're going to be good. So I'm going to say my initial amount's 2, so the half of that will be 1. I could have put 40, 20, 7,000, 3,500, but 2, 1 is so much easier. So let's just go with 2, 1. All right? If I take these three numbers here and substitute them into this equation, we end up with 1 equals 2e to the k times 14. Whenever you write down time on these problems, make sure you put a unit on your time. I don't care about units here. This is grams, that's grams, pounds, pounds, ounces, ounces, kilograms, kilograms. Okay, these don't matter so much. This matters, days. All right. So, is everybody okay with where I got all this from? I invented these two numbers just based on the fact it's a half-life, this should be half of that, and I know the half-life, I got that from page 425. So, can I do log both sides right now?
No.
No, because there's 2 in front of the e, so I'm going to divide both sides by 2, so 1/2 equals e to the 14k.
And I
I'm going to log both sides, ln of 1/2 equals 14k. Same deal, I'm going to do ln of e to the 14k. The e goes away, just leaving me the power of 14k. Divide both sides by 14, our half-life, and we get k equals, I calculator knows, the natural log of 1/2, in parentheses, because the log is over, divided by 14 equals negative 0.0495. I do want k to 4 decimal places. So again, I want nice fractions and stuff in your work. Once you get to the point where you're actually evaluating k, go 4 decimal places, round it for your value. Now they want the exponential decay function. So just the same way we did the exponential growth function, we had that beginning population of 16,400, right? Notice they don't tell us the beginning population here, right? We made it up, we said 2, but it's not supposed to be 2. What I want to do is, I'm a scientist working with phosphorus 32. I want to know if I have X amount of material for X amount of days, how much is going to be left after T days? That's what I want to know. So, looking at that idea, this and this and this are all going to represent variable amounts. If I know, if I can figure out how much this is, hey, Tucker, here's 500 pounds of phosphorus 32, you're going to keep it for 44 days. 500 pounds, 44 days, we should know exactly how much is left over at the end of 44 days, right? So that's what we're trying to create here. So the final amount of phosphorus 32 is going to equal the initial amount, which we don't know yet, but we can make up anything we want to. E to the k, which is negative 0.0495 times t. There's my exponential decay function, and I'm going to specify that t is in days. Make sure you identify that whenever you make these functions. How is t being measured? All right? Because again, that does matter a lot.